All right, welcome back. So today we are going to discuss improper integrals, which in spirit, I suppose, the nature of the word improper is sort of akin to how we use the word improper when relating to fractions. So here we've got the fraction of 3/4 and 5/4. I mean, 5/4 is still a fraction. It's just improper because of the way in which we define a proper fraction, being that the numerator is smaller than the denominator. So when we talk about improper integrals, they're still integrals. They're just not integrals in the proper sense. In the proper sense of an integral, we mean an integral where the fundamental theorem of calculus part 2 applies. So to remind us of the fundamental theorem of calculus part 2, if a function is continuous on an interval AB, then the definite integral, the exact signed area between the function's graph and the horizontal axis on that interval, evaluates to just capital F of B minus capital F of A. Now, there is a key assumption in there, and the assumption is that our function is continuous on the interval AB. And so, in some sense, there's sort of two violations to the fundamental theorem that could occur. One, what if you don't have an interval of the form AB, where you're including both endpoints, and both endpoints are just good old-fashioned numbers? Well, that would be a violation of the fundamental theorem. And another violation would be, what if your function wasn't continuous? What if your function had some sort of vertical asymptote on your interval of interest? So, keeping that in mind, that essentially boils down to two types of improper integrals. Two types of integrals where the fundamental theorem does not apply. So when we say, so let's break down these two types. So type 1 of an improper integral, an integral where the fundamental theorem wouldn't apply, is when you have an infinite interval. So here's an example, an integral from 1 to infinity. Oh my goodness, right? Now, to visualize this, if we're looking at the function 1 over x squared, I've got sort of an approximate graph of 1 over x squared over here. And if we throw in the point 1, which, about like so, then the interval from 1 to infinity is like all the way off the page to the right, just going forever and ever and ever. Now, in principle, it might seem like, hey, if I've got an infinitely wide region, I would have to have an infinite amount of area, right? But this function does sort of like descend towards the horizontal axis pretty rapidly, in fact. While 1 evaluates to 1, if you go over to x equals 2, you're evaluating to a fourth. X equals 3, you're evaluating to a ninth. So this function's hugging the horizontal axis. Maybe it's hugging the horizontal axis enough to where the area that's over off to the right is not infinite, despite the fact that the region is infinitely wide. And so it's sort of an interesting question to consider how much area is there to the right of 1 going all the way off the page between the function 1 over x squared and the horizontal axis. In general, if you have infinity as a bound of your integral, yes, it's still an integral, it's just an improper integral, because it's not of the form of an integral where the fundamental theorem of calculus would apply. The fundamental theorem of calculus demands AB, where A and B are both numbers, and you are including them. The interval of interest here, in this case, would be from 1 to infinity, which 1 comma infinity is certainly an interval of a different form than the fundamental theorem would demand. And so, in general, type 1 improper integrals are those where the interval is infinite, essentially an infinitely wide region of area. Type 2 form of improper integral are going to be integrals where we have an infinite integrand. When we talk about the integrand, that's just the function that's inside our integral. That's often referred to as the integrand. And well, 1 over x squared does become infinite. Check out a graph of 1 over x squared and think about its behavior. As x gets small, x squared gets small, the denominator. When small denominators occur, very small denominators, the fraction value gets very large. And that's what we see with this vertical asymptotic behavior at x equals 0. And well, hey, look at this integral down here. 0 is included as one of the bounds. And so in the case of the integral from 0 to 1, we are looking at the region between 0 and 1, between our function's graph and the horizontal axis. And because our function has a vertical asymptote at x equals 0, that means we are dealing with an infinitely tall region of area. Now, the function, just like it sort of hugs the horizontal axis off to the right, or I guess in a similar form or fashion, the function hugs the vertical axis as it's going to 0. That's the nature of vertical asymptotes. So again, it's sort of an interesting question to be like, well, hey, how much area is there on this infinitely tall region? Does the function hug the vertical axis enough to where that infinitely tall region only has a finite amount of area? Or is there enough space between the function and the vertical axis to where there is an infinite amount of area? Again, that's an interesting question. But yet that's a question that the fundamental theorem of calculus alone cannot address, because in the case of the infinite integrand, our function is not continuous on our interval of interest. Yes, our interval is of the form 0, 1, so that's not a problem. That sort of gets the check in a sense. But the issue is the continuity, right? So continuous, well, not on this interval, right? Because the function 1 over x squared is discontinuous on the interval 0, 1. So, right, particularly at x equals 0, we've got a point of discontinuity. So then the question becomes, well, hey, if these are integrals, despite them being proper where the fundamental theorem applies, how are we going to approach these to deduce how much area there is between the function's graph and the horizontal axis on these regions? And the strategy is we're going to use limits to resolve their evaluation. Give me a second to wipe the slate clean, and we'll touch base on how those limits manifest. All right, so let's touch base with the two precise situations that we saw before. One infinite interval, the other infinite integrand. So let's start with the infinite interval. Now, the issue here with this interval is really just the infinity. I mean, if we were taking the integral from 1 to a million even, going way off to the right, that's fine. 1 to a million is of the form AB, and the fundamental theorem would apply. If we took the interval from 1 to a trillion, that's perfectly fine as well. The issue is really just the infinity that's there. And yet, we can use limits to approach infinity. So the idea here is going to be that we will just fix the right endpoint of our interval at some b, imagining b being some very large number, a million, a trillion, something like this. And so what we'll end up doing is just consider the interval from 1 to b of 1 over x squared dx, where we'll take a limit as b goes to infinity. So imagine b going from a million to a trillion and even further. Well, then that would be perfectly fine. Now, b here is just a real number, which means the fundamental theorem applies inside this bracket. What we're going to do is apply the fundamental theorem inside this bracket and then work our way through. Just to remind ourselves, it's probably worth noting here, in the case of our little f being 1 over x squared, that's like x to the minus 2, right? If I wrote 1 over x squared, as x to the minus 2, well then antiderivative increase the power by 1 and divide by that power. You just have x to the minus 1 divided by minus 1, which would simplify to be minus 1 over x. And so that's x to the minus 1 power. Here is our capital F function. This will be helpful whenever we're applying the fundamental theorem, because, well, how would the fundamental theorem apply here? As it always would, capital F of b minus capital F of a. Well, a here is 1, so be it. And applying our antiderivative function accordingly, we would have minus 1 over b minus 1 over 1. So let's just call it a plus 1 over 1. And now this expression and applying a limit as b goes to infinity is just using the skills that you know already from Math 141. And so, or Math 132 at that. So whatever Calc 1 class you took. And so letting b go to infinity here, 1 divided by a very large number, is practically nothing. And so noting that minus 1 over b goes to 0, we just have 0 plus 1, which evaluates to be 1. And what is pretty darn cool about this is the region of area that is associated with this integral is indeed infinitely wide. And yet, this function hugs the horizontal axis enough to where the area that is in that infinitely wide region is only 1 unit of area. To say you'd only need 1 gallon of paint to cover that entire amount of wall board or something, or there's only 1 square unit of area all the way across to the right, which is almost crazy to think about when that area across the right is extending to infinity. But that is really a consequence of the fact that our function is just hugging the horizontal axis along the way. Interesting result, but the general idea here is, look, when you've got a bound that's infinite, just make the bound a real number and let that real number go to infinity. Work out the integral using the fundamental theorem, and then just let the limit do its job. Let's now swing over to type 2. So again, we're going to use limits to evaluate. In the case of an infinite integrand, when we have an infinite integrand, we're dealing with a vertical asymptote where our function is infinitely tall. Here we're looking again at the function 1 over x squared, but the bounds are between 0 and 1. Now between 0 and 1, we are incorporating our vertical asymptote there. We've got this infinitely tall region. So the issue here really with this integral is the zero. The zero is the problem. It's like, boy, I wish I just picked the zero to be something different. Like, what if I picked an a that was a little bit to the right of zero? What if I picked an a that was like 0.1, or an a that was like 0.01, or an a that was like 0.001? Well, as long as my a was anything to the right of zero, the asymptote is out of play, there's no continuity issues, and the fundamental theorem would apply. So if we consider the integral from a to 1 of 1 over x squared dx, we'd be fine, provided our a was to the right of 0. But we want our a to approach 0. Now, how can we make sure that our a is to the right of 0 and approaching 0? Well, we could make our a approach 0 from the right. Remember when we talked about limits back in Calc 1, you can have a limit approach a number from just one side. A one-sided limit is a perfectly fine thing. And in fact, it's a necessary thing in this case because we want to approach 0 from the right. If a were approaching 0 from the left, then a would be including on the interval a1 the vertical asymptote that we were trying to avoid. So in order to avoid our asymptote, we need to make sure that a is to the right of the asymptote so that as a approaches 0, we are not including the asymptote in our interval no matter the a we are dealing with. Since we are not including the asymptote on the interval from a to 1, that means that the fundamental theorem would apply. And so applying the fundamental theorem, as it always does, you just have capital F of the top bound, which is capital F of 1, minus capital F of the bottom bound, which is a in this case. And then, well, we just evaluate using our capital F function, which we've seen before to be minus 1 over x. So we'll get minus 1 over 1, which is minus 1, and then minus a negative 1 over a. Now, in this case, be conscientious to the fact that a is not going to infinity like b was. A is going to 0. So now this denominator is getting microscopically small, and microscopically small denominators yield gigantic fraction values. And so this fraction here is going to infinity, which means our limit would essentially evaluate to infinity. And when we have a limit that evaluates to infinity, the sort of standard word that we use to describe that is to say that the limit diverges. So this limit diverges. In general, a limit diverges whenever it does not evaluate to a real number. And so this limit diverges, which ultimately means the signed area between this function's graph and the horizontal axis on this infinitely tall region is infinite, which is kind of curious, right? Because we went infinitely wide with the function 1 over x squared, and we got only 1 unit of area. We went infinitely tall with 1 over x squared, and we got an infinite amount of area, which sort of suggests sometimes improper integrals are finite and sometimes they're infinite. Sometimes the integrals associated with improper integrals converge, and sometimes they diverge. And that's just life. But it really suggests that improper integrals provide a really interesting collection of integrals to consider. And well, this now gets us started with that vein of thought.